A tsunami is a series of waves caused by a sudden shift in the ocean floor. Although earthquakes usually cause such shifts, they can also be the result of undersea landslides, volcanoes, or even meteor impacts. In deep ocean waters, tsunami waves can travel hundreds of miles an hour, with little surface indication. But when the waves approach land, shallow waters can cause them to build up and form massive moving water called run-up. This run-up of water often rushes onto shore, striking the coast with tremendous destructive force. Generally, emergency planning calls for evacuation of the population to high ground before a tsunami can strike. However, in highly populated areas where higher ground may not be readily accessible, and/or where warning time is limited, vertical evacuation should be considered. A tsunami vertical evacuation refuge is a building or earthen mound above the maximum expected tsunami wave height, which is specially designed and constructed to withstand tsunami forces. A tsunami refuge differs from a traditional disaster shelter because it is meant to be short-term, just until local authorities allow residents and visitors to carefully exit to a safer location. The key is the building's height and its strength to withstand the wave and debris impact. There are 5 different types of forces that a tsunami vertical evacuation refuge must be designed to withstand. Hydrostatic forces occur when standing or slowly moving water on one side of a structure is deeper than the water on the other side, with the weight of the water causing an imbalance of pressure. Buoyant forces apply pressure vertically when watertight structures are submerged. The total amount of buoyancy force equals the weight of the water displaced, and water weighs over 8 pounds per gallon. Buoyant forces increase quickly with the depth of water and are a concern for structures that have little resistance to upward forces, such as light wood frame buildings, basements, and empty tanks. Hydrodynamic forces, also known as drag forces, are caused by the flow of water moving at moderate to high velocity. Fluid density, as the underlying sediment is shaken up in a tsunami, and the speed of this flow, as well as the structure's geometry, are all factors to consider when calculating the hydrodynamic load on a structure. It is a combination of the pressure from the moving mass of water and the friction generated as the water flows around the structure or component. Debris impact forces, such as floating driftwood, lumber, boats, shipping containers, automobiles, buildings, and other floating debris, can also cause serious damage. The design must avoid the potential for progressive collapse when a column is damaged by debris. Dams created by waterborne debris add to the hydrodynamic force by displacing water that had been flowing around the structure. Tsunami-resistant structures will have strong systems with the reserve capacity to resist extreme forces, which would include the generating earthquake as well as the tsunami loads just described. Open systems that allow water to flow through with minimal resistance. Ductile systems that resist extreme forces without failure while remaining functional. Redundant systems that can experience partial failure without progressive collapse. And a foundation capable of withstanding tsunami loads, and designed to account for erosion, subsidence, and long-duration shaking from an earthquake. Buildings made with reinforced concrete and still moment frame systems and reinforced concrete shear wall systems oriented parallel to anticipated tsunami flow fit these criteria. In addition to structural design, those planning for vertical evacuation facilities should consider accessibility, including accommodations for individuals with physical disabilities, parking, pets, occupancy limitations, and the protection of critical functions, such as emergency power and provisions such as food and water. Building a structure that can serve as a tsunami refuge will cost on average between 10 to 20% more than a building without these extra precautionary measures. While retrofitting a structure for vertical evacuation could also be expensive and disruptive, it may be viable if the original building is of heavy construction, such as reinforced concrete, and was designed to accommodate ground shaking as well as the excessive forces associated with wave action. And newly constructed buildings or structures engineered to withstand tsunami forces have the added benefit of being capable of surviving a preceding earthquake, as well as the most extreme coastal storms. This building would help keep the public safe and sound from multiple hazards present along coastlines. Vertical evacuation is one of many hazard resilience strategies to be considered during the risk mapping, analysis, and planning effort in your community. If you're considering building or retrofitting a structure to be a tsunami vertical evacuation refuge, then have your architect or engineer consult FEMA P646 Guidelines for the Design of Structures for Vertical Evacuation for additional information.